How we going, guys? Coach Gregory from Based Wrestling. Okay, so this video forms part of the series which covers the studies that we do at Edith Cowan University in the Bachelors of Sport Exercise Science. I did this as a project as part of my degree. Okay, so as I've gone through these units, this is exactly the review material that I have used. I think at the moment I'm tracking somewhere between distinction and high distinction. So it kind of works. It's relatively decent. It's not a guarantee by any means, but let's just say that it's enough to give you a fairly decent sort of base to work from. So if you're considering getting into exercise and sports science, this should be quite helpful. If you're currently studying it and you need some review material, this should be quite helpful. If you're in a remote or overseas area where you don't have access to this, like the degree level courses, or it's too expensive or something like that, then this is here to help you. That's what we're all about. We like helping people. We like it. We want to see the sport grow. And for that to happen, coaches at all levels need to be able to access knowledge to improve their player outcomes, which is what this is all about. So stick around, hope you enjoy it, and let's get into it. How are you going, guys? Coach Gregory from Based Wrestling. Alright, so as you heard in the intro video, this is a part of a review process that I've done during my studies at Edith Cowan University, Bachelors of Sport Exercise Science. So this is Nutrition 1. You'll do this in first semester. The unit code, if you're interested, NU 1121, and it's human nutrition. So let's crack on to this. So why are we doing it? Basically, so this can be done. So what I did this as part of a review process for myself for my semester for the exam. You could do it as a preview to get an idea of what you're walking into before you walk into it. It's always a good idea. To develop your knowledge as a coach, so a lot of our coaches are community level, they work, or they're in remote communities, or even overseas in places like Zambia and those sorts of things, where you don't always have access to high quality universities. You can't afford to take time off work, travel, you don't have a reliable internet connection. So this is for you guys as well. And also, if you're part of our youth program and you're thinking about going into exercise and sports science, then this is an opportunity to look at exactly what you cover in that unit, what's involved in it. So the main reference tools that they use in this, okay, are Understanding Nutrition. That's a book by Eleanor Whitney. I think it currently we're up to Rev 5, Rev 6. Don't stress too much. I did this with a Rev 5, a Rev 3 version. There's some differences in page numbers. The statistics have been updated, but the fundamental principles that govern it haven't changed at all. Okay, and a lot of the page numbers, a lot of the diagram numbers are all still the same. So don't stress too much. What's important is you've got the reference material there that you can go through, because your lectures will follow the chapter structure of the book. Okay, so make sure you're doing your reading. That's important. The other tools you'll get access to as an ECU student, you'll get free access to FoodWorks. Okay, that's a dietary management software. You need to be across that. As a student of nutrition, you must have your head around that and know what you're doing. Okay, because you've got labs on that, you've got assignments and exams on that. So if you're on campus, make sure you're getting to your lectures, make sure you're getting to your labs. If you're off campus, friends, family, co-workers, anybody, get them to use the app and get you some data for FoodWorks that you can use, that you can go through, look at, and understand what that information's telling you. Get practice putting in recipes, get practice changing things in a person's diet, and see what effects that is going to have. How can you improve their results? Okay, and also understand how the software works, what it likes and what it doesn't. So that if, when you're doing your assignment for it or your assessment for it, something goes wrong, you're able to go, yep, no, seen that before and I can fix it. Okay, the other tool you get access to as a ECU student for free is Studiosity. Now, full disclosure here, guys, I don't use Studiosity personally. Okay, it's not my thing. I'm much more, I will go and annoy lecturers or librarians or whoever I need to get the help that I need. I'm a more face-to-face type person. But other students on my in my cohort, they use Studiosity and they love it. So try it, see if it works for you. If it's something that you like, then by all means use it, because that's what it's there for. Alright, so on we go. Section 1, Nutrition Basics. Alright, so this is week 1, this is what you get. And all the fluff has been pulled out of this to leave the bare bones basics. Alright, cool, away we go. So what we're going through, key points for this session. Factors that affect a person's food choice. Classes of nutrients. Nutritional reference values. Okay, you need to understand those. How we assess nutrition status. Risk factors for chronic disease. And how we can identify misinformation. That's pretty much what's in it. So, factors affecting food choice. So, cultural practices. Okay, so if you've got friends who are Muslim, Ramadan, these sorts of things. Members of the Sikh community, Catholics. You know, different places have different cultures and traditions. Food availability is a big one, particularly in remote communities. Okay, not all food is available all year round. Social situations. If your thing is to go out on the Friday night for pizza and beer with the boys, then that might be a social situation. Well, you know, it's not really the done thing to go and order a salad when it's pizza and beers. And that social pressure can affect your food choices. Habits. If your habit, for example, is I get up in the morning and I have my coffee, well, that just becomes one of those things. That's what you do. I get up in the morning, I have my cereal and my coffee, or my bacon and eggs, my coffee. So habits do dictate a lot of what we do. Emotional attachment. This is the one, if you're familiar with the old thing of, you know, the breakup ice cream. You know, have a bad day, have a breakup, and the trope is that the person's pulling out the, you know, bucket of ice cream to chow down on that. Okay, and it's just it's a comfort, what they call a comfort food. Okay, personal preference. Okay, I may prefer white bread over wholemeal bread, for example. Yeah, is it healthy? Not really. Should I be eating wholemeal bread? Probably. Okay, would that be better for me? Probably. Okay. So the other one that's not in here that I think probably should be medical conditions. Okay, so your medical conditions and your health status can drastically affect what you have to eat. Okay, and so the big one to remember here when you come across this question in the exam, because you will, okay, why do you eat what you eat? Put it in that framework, understand why you do what you do, and answering that question becomes easy. All right, nutrition. So what is it? It's the study of foods and how the body handles them. That's it. It's that simple. Why we eat, what we eat, and what happens when we do. That's fundamentally, that is what this entire thing is. The entire 13 weeks, that's what it's about. Okay, so nutrients. Right, there's 2 different ways we can break this down. Okay, we're going to go through the first one, which is organic and inorganic. The second one we'll go through is macros and micros. Macronutrients, micronutrients. Okay, so organics, these contain carbon. Okay, carbohydrates, proteins, fats. Get used to calling them lipids, because that's a term you're going to hear all the time. Lipids, okay, and vitamins. Now, inorganics are water and minerals. Okay, they do not contain carbon, hence the term inorganic. All right, macros and micros. These are the terms. If you've been in the fitness industry at all, these are terms you're going to get familiar with. As you go through this, get familiar with these terms. Okay, macros are energy yielding nutrients. Okay, that's important to remember. Okay, and they're required in large quantities. Okay, because we need a lot of energy to keep going. The numbers you need to remember these. Okay, protein and carbohydrates, 17 kilojoules per gram. Okay, lipids, 37 kilojoules per gram. Okay, you must remember those numbers. Must. Okay, not just for this unit, but for other units as well. So get that number through your head. Okay, remember them, write them down. I would say get them tattooed on your arm, but that would be bad advice. Don't get them tattooed on your arm. Okay, other stuff, by all means, go for your life. But so micronutrients, these are required in minor quantities. They do not yield energy. Vitamins, minerals. Okay, and obviously we haven't mentioned water here. Water sort of isn't really a macro, isn't really a micro, it's just water. Okay, and a side note there, alcohol, all alcohols yield 29 kilojoules per gram. Okay, so now remember, we're not just talking about having a beer. Okay, there are alcohols that are used in other parts, as you'll find going through this, but same again, they yield 29 kilojoules per gram. Okay, sugar alcohols, for example, are an example. Yeah, it's not a sugar, so it doesn't fall into the carbohydrate realm, but it's an alcohol. So even though it's not sugar, it still yields more energy than the standard simple carbohydrate. So it's actually, in terms of kilojoules and weight gain, it's actually worse for you. Okay, so be aware of that. You need to know that number. You do need to remember it, but it's not mission critical. It's not going to completely wreck you. Okay, but the 17 kilojoules per gram for protein and carbs and 37 kilojoules per gram for lipids, you must know them. All right, cool. Moving on. All right, nutrition reference values. Okay, the big one, upper limit. That is when it becomes toxic. Okay, that is the do not exceed this limit. All right. AI, adequate intake. Okay, this is what is considered the bare minimum. We don't want to go below this because that's when we're going to have to get problems with deficiencies. Estimated average requirement, EAR. Okay, that is the recommended or the required amount for 50% of the population. Estimated. Okay, it's a vague, rough idea. Use this number if we don't have anything else. Okay, RDI, this is a recommended daily intake. This is the one that we want to use where possible. Okay, when something's got an RDI, we want to be aiming for this RDI. This will cover 96 to 97% of the population. Okay, if we don't have an RDI, we'll use an EAR. Okay, at a bare minimum, we want to exceed the adequate intake. All right, and we don't want to exceed the upper limit. Easy as. You need to know those. Okay, AMDR, acceptable macronutrient distribution range. Okay, you need to know this. Okay, you need to know it, need to understand it. Okay, it's the macro breakdown. Okay, the spread of energy yielding nutrients that we need to aim for to stay in a healthy range. As a coach, we manipulate this to change our weight. You know, if we would need to gain weight, lose weight, how we want the body to manipulate its situation. So having an understanding of this is important, yeah? So carbohydrates, 45 to 65% of our daily energy intake needs to come from carbs. Protein, 15 to 25% of our daily energy intake. Fats, 20 to 35%. Okay? So if you're used to dealing with gym buddies, you'll hear the whole 60-20-20 thing. Okay, this is where it comes from. 60% carbs, 20% protein, 20% lipids. Okay? It's a quick, easy, dirty way of working out your energy spread. Okay? High carb, high protein, low fat. Boom, away we go. Okay? So I use that 60-20-20 because it helps me just get a vague ballpark of where I need to be. And then I go up and down to work out my exact spread that I need when I get the question, what should it be? Yep. So I know my carbohydrates got to sit around about 60%. So 65 is my upper, 45 is my lower. Easy. Okay? All right. Cool, moving on. Nutritional assessment in individuals. There's 4 ways we can go about this. Historical information. That could be the person's personal history, or it could be in relation to the population that they come from. Okay. Anthropometric data. These are our measurements of our body measurements. limb lengths, height to weight ratios, body fat percentages, all that sort of stuff. Physical examinations, okay, usually these are done by a doctor, okay, but looking for things like skin lesions, problems with nails, problems with discoloration, visual issues with the eyes, that sort of thing. And finally, laboratory tests, okay, so this is when you get your bloods done, okay, or, breath testing as well can be another way of doing it, saliva testing, all sorts of stuff, okay, so again, done in labs. So when we talk about nutritional assessments on populations, okay, there's a few different ways we can go about testing things. We have epidemiological studies. So these are big studies covering whole populations, okay, wide-ranging, usually over the span of years. They give us really good ballpark data. As a general rule, 50% of X population just has issues with this particular illness. Okay, that might be diabetes, that might be alcohol, that might be fetal alcohol syndrome, lots of different things. But these are epidemiological studies covering either an entire country or a population within a country, a tribe, a community, a particular racial group, a particular group from a particular area or a particular town. So Bureau of Stats are really good for this. Okay, so lab-based studies. These are highly controlled, usually focusing on like cell cultures up to animal testing, okay, to determine effects of drugs, effect of different, antibodies and that sort of stuff. So it can still be used to determine changes in diet when we change the diet of certain animals to see what happens to them. And then finally, we've got clinical or human trials. These are trials that you can actually get involved in, okay. Do be careful if you are going to get involved in human trials and testing. It is quite an experience, but depending on how they're run and what you're dealing with, can be problematic as well. Okay, so just be careful with that. But they provide near real-world situations. Okay, so it's usually the last phase before a product is released, and it's aimed at getting an idea of what is this thing actually going to do when a real person gets hold of it. Are they going to use the product the way we want them to, or are we going to get something like take one tablet 3 times daily and the person takes 3 tablets all at once, or misses 3 days and then decides to take 9 tablets all at the same time? How average is an average human? Okay, so it gives us how the product is going to interact with the person's real world scenario. Okay, they wake up in the morning, they have breakfast, and breakfast might be a piece of toast and half a slurp of coffee walking out the door at the same time as taking their tablet. And that may not have the desired result. Okay, so those sorts of things is what that's all about. Scientific method, okay, so you need to understand this. Not too critical in the early stages, but as you go through, this is going to become more important. So we start with an observation and a starting question. Looking at a situation, determining, sitting there going, okay, that was a bit weird, why'd that happen? Then we have a hypothesis, and it's a statement. It's a statement of a predicted result. When this happens because of this. Boof. Not questioning, not asking. We're saying that because the person doesn't lift heavy enough weights, they're unable to perform at elite level. True, maybe, maybe not. Let's find out. Okay. We then design an experiment to challenge the statement. The experiment's not to reinforce the statement. The experiment is an attempt to disprove the statement. Okay, that's important. We're not looking to validate our own statement. We're looking to disprove it. We want to be the devil's advocate. Okay, so we conduct the experiment, we analyze the results, and then we follow it with the question: is the statement correct? What does the evidence say? Is it right? Is that statement okay if they do not lift heavy, they cannot perform at elite level? True? False? Don't know. Somewhere in the middle. Okay? Or the ever popular S&C coach answer, if you're in the world of S&C, depends. Okay? If yes, then, well, we develop our theory and we start to expand upon that to gain some more clarity and depth to it. If it's no, well, we go back to the start and around we go again. Okay? If it's a maybe, well, then we need to drill into that subject further to better understand why, we got some performance, but we didn't get exactly what we were expecting to get. So there's some truth in this maybe, but this can't be the whole story. And then we have to follow that down the rabbit hole to better understand the topic that we're looking to research, yeah? Cool. All right, so risk factors. Number 1, top of the list, smoking. Second, alcohol. Third one, physical inactivity. And then oddly enough, 4, 5, and 6 all seem to have close ties to the first 3. High body mass index, or BMI, if you're into that. High blood pressure and high blood glucose, blood sugar. Okay, you need to understand those. You need to know what they are. But the easiest way, start with the top 3. Smoking, alcohol, physical inactivity, which will lead you into the next 3. High BMI because of physical inactivity, or potentially and or smoking and or alcohol. Blood pressure because of smoking and or alcohol and or physical inactivity. Okay, blood glucose level, raised blood sugar because of probably poor diet, but probably also related to physical inactivity because we're not getting enough exercise and therefore we're getting storage of glucose, leading to high blood glucose. Okay, so use one or use the first 3 to feed into the rest. Determining fact from fiction, so this is getting into our spotting misinformation. So the good stuff, good examples of what you're looking at. Research journals are going to be peer reviewed. Okay, there'll be reputable things, PubMed, what's some of the other ones? Journalist, Sports Science, what's the other one? JSMC, Journal of Medical, JMRC or something like that. So yeah, there's a lot of them. If in doubt, go to the library. That's what it's for. They've got a whole bundle of research articles and research resources for you. And if you are doing postgrad studies, there's even more available to you. So don't be afraid to get in there. Okay, plenty of online stuff available through them as well. Objective studies. So we're talking about blind and double-blind studies. Not always possible, but where you can do blind and double-blind studies, that's the best way to go. Okay. Respectable cohort sizes. It can be difficult sometimes when you're doing research to get large cohort sizes, but more samples give you more consistent data. It's going to give you a better picture of what's going on. If we only got 10 people, then one weird result is 10% of your results. Okay, whereas when you're dealing with 100 people, one weird result, one person is a little bit different from all the rest, that's only 1%. It's not going to contaminate your entire pool and skew the results in a weird direction. Okay, qualified authors, and they're not afraid to be named. Okay, good researchers like to do good work. Okay, we like to publish good work and we like to have it recognized and we like to be acknowledged for that. If a researcher is not prepared to put their name to a paper, or a reviewer is not prepared to put their name to it, then there's probably a good reason for it. Okay, so be aware of that. So what we just covered, right? The factors affecting people's food choices, classes of nutrients, nutrition reference values, how we assess nutritional status, what are the main risk factors for chronic disease, and how we identify misinformation. All right, so that's everything we've just gone through. That's what you're going to cover in week 1. All right, useful links you're going to find. So Australian Dietary Guidelines, Dietitians Australia, and also Nutrition Australia. If you're first coming into this, and even if you're only working at like a local level, the dietary guidelines are well worth your time to get your head around because they're very, very useful. And when you're dealing with young clients or clients who have no idea about diet and eating and these sort of things, send them there. Okay, it's decent information and it's well researched and well backed up. Okay, so what's good of everything we just covered? What kind of questions are you going to get? Okay, these are examples of those. Okay, 4 things that determine a person's diet or dietary choices. or worded something like that. Okay, so we had things like cultural, social situations, emotional attachment, food availability, medical conditions, personal preferences, habits, etc. Okay, heaps of know those. Okay, 3 common risk factors for chronic disease. So remember the top 3: tobacco, alcohol, physical inactivity. Okay, boom, easy. Okay, easy marks. And then you've got, you know, high blood glucose, high blood pressure, and a high BMI. So be aware of what those are. Make sure you understand what they are, how it all fits together, because that will come up in your exam. Okay, from the panel opposite. Okay, so we've got looks like a peanut butter jar. Okay, what's the energy in kilojoules from fat per serve? Okay, so there we can find the total fat listed, so 11.9 grams looks like. Okay, remember, from fat, 37 kilojoules per gram, so 11.9 multiplied by 37, and that'll spit out that number for you. It may not be exactly that question, but there'll be a question, at least one, if not more, on working out different energy, the amounts of energy produced from different sources in different diets and that sort of thing. Okay, you're going to run across this all the time in this unit, so you need to have your head around that. All right, cool. Take a break, and we'll get into the next bit. Okay, so hopefully you got some food, bit of a drink, brain break. So this is what they're going to cover in week 2 of your nutrition unit. Okay, so what they're looking at here. Okay, so we're looking at the difference between digestion and absorption. Okay, we're looking at the different roles of the parts of the digestive system involved in digestion. Okay, so we need to understand the process and what's actually happening. Okay, so comparing and contrasting the processing of carbohydrates, proteins, and lipids. Basically, what happens where and when, and how it occurs. Okay, they're laying the groundwork for what you need going forward. All right. So 2 main roles of the gastrointestinal tract, or the GI tract as it's known. The GI tract is flexible muscular tube running from the mouth all the way to your anus. Okay, its main job is to convert food into nutrients. That's what it's there for. That's why we've got it. And finally, to remove waste from the body. Okay, so once it's done with everything, anything that's not required is removed. Okay, so the flow of nutrients, right, you must know, right, you'll find this image, picture, whatever you want to call it, you'll find it in the book, okay, in Understanding Nutrition. I'll say it, they're going to say it, okay, you must know this. You must understand, must know it and understand what we're talking about. Okay, so mouth to esophageal sphincter, so that's when your food is basically goes through its first mechanical breakdown, and then it becomes a bolus. Okay, need to know that term. Okay, from the stomach into the small intestine, large intestine. Once it leaves the stomach, enters the small intestine, it is no longer a bolus, it is now called chyme. Okay? It remains as chyme all the way through until it becomes feces when it is excreted out of your anus. Okay? Happy with that? That's basically where it's at. Okay? So the flow of food, so we're going from the mouth, esophagus, small intestine, large intestine, rectum, anus. Remembering the parts of the small intestine, the duodenum, jejunum, and ileum. Okay. You need to know the order, and you need to have a vague idea of what each of those is doing. Okay. So, but above all, that image, that page, you need to know it. The information that's on there, the flow of food and how it works, what happens where, you need to know it. Okay, so get across that. So digestion. Okay, so digestion is the breaking down of food to nutrients. Occurs by either mechanical or chemical means. Okay, so there are two processes that are happening. When we talk about absorption, absorption is the transport of nutrients across the epithelial barrier for utilization. So transporting it out of that muscular tube into the rest of the body, okay, for further utilization. That occurs by chemical only. Okay, there's no mechanical means, there's no opening and closing of valves and this sort of thing. Okay, it's all occurring at a molecular, or molecular level, effectively. Where chemicals are being changed and transported and moved backwards and forwards. Okay, as opposed to digestion, which is simply the process of it moving through that muscular tube. With absorption, we're talking about the movement of the nutrients and the stuff that we need from the muscular tube, the GI tract, out into the rest of the body to either our lymph system, our circulatory system, etc. for transport and further utilization. Okay? Got to know that. Okay, so parts of the GI tract, spoke about this already. So the mouth, its primary role, break up food into smaller units. Saliva begins a breakdown of simple sugars, okay, simple carbs, and this is where the bolus begins. Okay, this is what starts to form a bolus. Okay, esophagus, basically its whole job is to transport the bolus from the mouth to the stomach. Okay, esophageal sphincter, that is at the top of the stomach, and that's basically to prevent anything in the stomach from coming back up, okay, unless it's absolutely critical. Okay, so if you start to have problems with reflux, this can often be part of that. Okay, there's something wrong with the esophageal sphincter and it's not really doing its job the way it's supposed to. Okay, stomach, so addition of acids and enzymes to turn the bolus into chyme. Okay, so this is where it basically turns the semi-solid mass that we had before into a more liquefied version. Okay, from the bottom of the stomach, the pyloric sphincter, okay, that controls the passage of chyme into the small intestine. Okay, this is what breaks it off into pieces so that it's manageable for the small intestine to transport it through. Okay, the small intestine, round about 3 meters long, the three parts, duodenum, duodenum, ileum. Okay, acids and enzymes are added from the gallbladder in bile acids and the pancreas, pancreatic acids, and they've each got roles to absorb different nutrients and enzymes. Correction, the enzymes have roles to absorb different, break down and absorb different nutrients into the blood and the lymph. Okay, that's the whole job of the small intestine. Okay, you got the good grief, don't get angry if you get this wrong, hey, because it's ileocacal valve. There we go. It's another sphincter, okay, and that controls the passage of material to the large intestine. Okay, so at each stage we've got steps in there to control just how quickly everything's moving through. All right, in the large intestine, so we're reabsorbing water and minerals, and we're passing waste, bacteria and fibers and non-absorbed minerals to the rectum. So basically it's a last stage processing, like a SCAV circuit. Okay, so it's just recovering what it can to recycle. Okay, and our rectum, basically we store waste water and material here, and then the anus basically holds the rectum closed until we're ready to eliminate waste. Go to the toilet. Okay, that's it. Got to know that path, got to know what each of those elements in there do and how they do it. So the digestion process, so again, going back to the start, look at this again, but from a different perspective. So we looked at the pathway of it before, now we're going to look at what happens at each stage. Okay, so in the mouth, carbohydrates, you'll find them abbreviated as CHO all the time. Okay, get used to that seeing that, identifying carbohydrate, CHO, yep, cool. Okay, so CHO, digestion begins here with salivary enzymes. They begin the breakdown of simple sugars. Okay, fiber and others are broken down manually. The process called mastification, basically chewing your food. Okay, in the stomach, the breakdown of carbohydrates stalls due to the reaction between gastric acids and salivary enzymes. So if it hasn't broken down the simple carbs by the time it gets to the stomach, It's not getting broken down any further in the stomach. Okay, protein breakdown begins due to the gastric acid. Okay, and also in that process, our fats are going to float to the top due to the liquid, and so that's where we get that layer. So we're starting to get some separation happening here. Okay, in the small intestine, our carbohydrates, our sugars begin immediately to transverse the intestinal cell wall. Okay, they're easy to transport, they're simple. Okay, hence the term simple carbohydrates. Okay, starches are broken down to be transported by pancreatic enzymes through the cell into the hepatic portal vein. Okay, so they can be moved back in and circulate through the blood, so they can then be broken down to become, glucose effectively. Proteins, our protein breakdown continues with the rate depending on the pancreatic acids and intestinal proteases. Okay, so they're like they're catalyst enzymes, basically. Okay, so as you're going to find out in different units, different enzymes and different proteins interact. Okay, so, and proteins made up of multiple amino acids, and don't worry about it. You'll get into that later on. Okay, don't stress. But what's important now is that protein breakdown begins in the small intestine, and it's specific enzymes that transport specific proteins. Okay, smaller proteins and amino acids are absorbed into the hepatic portal vein. Okay, same, fats and lipids. Okay, so bile breaks down lipids, so they can now be processed as proteins. Okay, so basically, fats, our lipids are, basically massive storehouses of effectively proteins, which are then storehouses of glucose, effectively. Okay, so that it'll begin this breakdown process so that it can start to actually transport them as proteins and aminos. Vitamins and minerals are also absorbed in the small intestine as much as possible. Okay, so large intestine, so we've moved on from the small intestine, we've now got the chyme moving into large intestine. Our fluids and our minerals, some minerals that are missed in the small intestine, they can be absorbed here. Okay, so this is the last stage. Fluids that are not, that can be salvaged and are not required for waste removal, they're reabsorbed here as well. Okay, our fibers, our soluble fibers, so soluble fibers are sort of become gel-like when exposed to water. Okay, they can be reabsorbed here. Some resistant starches can be. Most fibers, most resistant starches will pass through here without being absorbed. That's what gives your feces structure. Okay, if there was no fiber, if there was nothing there, you'd be squirting the whole time. Excuse me. All right, so how does it all happen? So basically, we've got this picture here. You'll find it in the book or something similar to it. So what we've got is the goblet cells on the villus. They take in our different things we want to absorb. Excuse me. Okay. And depending on what it is transported through, and then it either finds its way into the vein to be reabsorbed, or it finds its way into the lymph system and is then transported through that way. Okay, remembering we've got the two systems working side by side here. So we've got a circulatory system and a lymphatic system. You'll learn about those in Anat and Phys. Don't stress, but it all links together. Okay, always remember with all this stuff, it all ties into the same thing. Okay, we're working wholly and solely on the human body. We're optimizing human performance. Okay, so the hepatic portal vein. Okay, you may or may not get nailed with this during the exam, but it's definitely worth understanding what's actually happening here. Okay, so basically this pathway is all about transporting nutrients from the small and large intestine into the circulatory system so they can then go through kidneys, liver, and anywhere else that happens to be needed in the body. But if we can't get it out into the circulatory system, it can't get where we need it to be. Okay, even our lymphatic system eventually dumps back into our circulatory system for processing through liver and kidneys. Okay, because they're the ones that remove all the contaminants. Okay, so this picture you will find, or something similar, you'll find in the book. Okay, so read it, understand it, know what you're looking at. Okay, even if it's not in the exam, understanding this will help you in the exam. All right, cool. Moving on. Okay, so what we just covered. So the difference between digestion and absorption. We looked at the roles of the parts of the digestive system involved in digestion. Okay, and we compared the difference for the processing of carbohydrates, proteins, and lipids. What is broken down where and how. Okay, but remember, digestion is the process of moving from mouth to anus through the tube, muscular tube. Absorption is the process of the movement of nutrients from the GI tract into the rest of the body. Okay, got to understand that. Okay, so when does the breakdown of carbohydrate begin and by what? Okay, so remember that's occurring in the mouth. Your salivary enzymes are the first things to start breaking down simple carbohydrates, and it stops when you get to the stomach, only to restart again in the small intestine. Okay, understand that. Okay, where does protein breakdown happen? Just gave you the answer, small intestine. Okay, how are fats and lipids broken down and transported, and to where? Okay, so fats and lipids, the initial separation begins in the stomach. The breakdown happens in the small intestine. Okay, understand that. Okay, transportation happens via goblet cells in the small intestine. So the fats are broken down into proteins and then transported as proteins. Okay, triglycerides basically. Okay, what is the structure that facilitates nutrient transport in the small intestine? Okay, so that's going back to that drawing, that picture that we had of the funny elongated, I don't know what you call it, thing. Okay, so you have your villus and covered in microvilli. Okay, so it's your microvilli that is, and the goblet cells on the microvilli that are transporting those nutrients into your lymphatic or circulatory systems for them to then be transported around the body. Okay, good stuff. All right, take 5, and we'll get on to the next bit. Alrighty. Okay, so week 3, what they're going to look at. Okay, our focus for this one. Energy calculations and your acceptable macronutrient distribution range. Remember that from first week. Okay. Carbohydrates. Okay, so what's a carbohydrate? What are complex carbs? What are simple carbs? What are intolerances and how do they work? Fiber. What are the different types of fiber and what are the health effects of fiber? Alright, so let's get into it. Okay, so your AMDR, your acceptable macronutrient distribution range. Again, cast your mind back, first week. 45 to 65% for carbohydrates, 15 to 25% proteins, 20 to 35% lipids. Okay, so there's 2 ways we can go about calculating what we need here. One way is what they call basal metabolic rate, BMR. Okay, some people swear by BMR. I tend to swear at BMR. Okay, I'm not a BMR fan personally. Okay, I don't believe it gives the right number that you need. Okay, TDEE, total daily energy expenditure. That is the amount you actually need for an entire day. Okay, your basal metabolic rate is the amount of energy your body needs just to sustain life. That is lying down basically unconscious. Okay, breathing, respiration, blah, 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 nothing else. As soon as you move your hand or anything else, that's screwed that number. That's messed that up completely. Okay, so your BMR is the absolute drop dead bare minimum. Okay, as opposed to your total daily energy expenditure, which is what you actually use or pretty close to it. Okay, always remember, this is 90% of this is bucket chemistry. Okay, it's something like that. About, it's by no means accurate, okay? Because life isn't like that, okay? My TDEE varies from day to day to day depending on what I'm doing, how hard I'm training, how stressed I am, how well I slept, how long I slept, my heart rate, my respiration, the whole, yeah. So it's not set in stone. They're not accurate, super realistic numbers. Okay, this is all bucket chemistry. Okay, but you need to understand what they are. So your BMR is your bare minimum, basically unconscious. Okay, total daily energy expenditure is what you're actually burning in a day. Okay, or pretty close to it. So how's it done? So we're going to take female, 18-year-old, high activity and training load. So this person's an athlete. 70 kilograms, 165 kilos, 15% body fat. So they are, for a female, pretty lean. Okay, there's not much in them. Okay, estimated 3,145 calories. Hang on a second, that's a problem. We need this in kilojoules, not calories. So 1 calorie is equal to 4.184. Okay, 4. All right, so 3,145 multiplied by 4.184 in this case. But look, if you remember nothing else, 4. Okay, 1 to 4 ratio. That's all you got to remember. Okay, so total daily energy expenditure for this individual, 13,158. Or correction, 59 kilojoules. Okay, so they crank through it. Okay. So if we're going to take this and we're going to say, okay, they need 55% carbohydrates. Okay, we're just picking a fluffy number here. Okay, don't crucify me on this. Okay, 55% carbohydrates. Remember back, our carbohydrates and proteins, 17 kilojoules per gram. So how many grams of carbohydrate does this athlete need? So we've got our 13,159, we're going to call it, because we're rounding up. Multiply that by 0.55 for 55%, and we're going to come out with 7,237.45 kilojoules of their energy needs to come from carbohydrates. Okay, so we worked out how much energy they need from their carbohydrates. Now to get that to grams, divide it by 17 kilojoules per gram, which spits out 42 or 425.7 grams of carbohydrates. Now I can tell you for a fact that this athlete, that's pretty much about what they go through. Okay, close to half a kilogram of carbs every single day. Okay, if not a bit more. Okay, so, but that's what they need. You know, they're training multiple times a day. They lift weights. They got technical training as well. That's what an athlete of that caliber is going to go through, if not a lot more. Okay, so this is why we're doing it. This is the purpose behind it. The reason for this AMDR stuff and total daily energy expenditure is so we can work out just how much fuel does this person need. All right, so types of carbohydrates. So we've got simple and we've got complex. So our simple, we're talking about what they call monosaccharides, single sugar, and disaccharides, 2 sugars. Because mono, 1. Di, 2. Poly, more than 2. Okay, then we've got complex carbs. These are polysaccharides. Okay, more than 2 sugars. Okay, glycogen and starches. Boom. Simple as that. But we will get into it more. Don't stress about that. Okay, so our simple carbohydrates, our monosaccharides, what you need to know. 3 types: glucose, fructose, galactose. Must know them. Understand those, know those 3. They lead you to all the rest. Okay, so disaccharides, you've got maltose, which is a glucose and a glucose. Okay, lactose is a glucose and, oddly enough, a galactose. Yeah, it's in the name, yeah? And you got sucrose, which is a glucose and a fructose. So remember, they've all got the glucose in them. Maltose, double glucose. Lactose, glucose and galactose. Sucrose is a glucose and a fructose. You need to know those. You need to understand how they fit together. Okay? Understand that. That makes a lot of other stuff easy, and it's easy marks. Okay? Disaccharides form by condensation reactions. Okay? So they produce water when they are formed. Therefore, when they're broken down by hydrolysis or adding water. So they dissolve in water. Okay? So you take your sugar, your teaspoon of sugar, you put it in your water, and it dissolves. Because, like we've just seen, disaccharide bonds, sucrose, which is your table sugar, glucose and fructose, is formed by condensation. Therefore, add water to it, and guess what? It breaks down into glucose and fructose. It's no longer sucrose. You broke those bonds, it becomes glucose and fructose. Understand these, and this stuff becomes easy. Okay, so disaccharide decomposition. Okay, each disaccharide is also broken down or by a specific enzyme that facilitates the breakdown. So the body needs to conserve energy, and this is how it does it. Okay, it uses catalysts all the time. Okay, your enzymes that break down things can be identified by the suffix ase. Okay, ase. So maltase is there to break down, wait for it, maltose. And it breaks maltose down into glucose and glucose. Straightforward. Okay, lactase, surprise, surprise, is there to break down lactose. Lactose gets broken down into glucose and galactose. Big surprise. Okay, and then sucrase is there to break down sucrose, and it breaks down sucrose into glucose and fructose. Both. Easy. Like I said, understand those first three, and everything else flows downstream from that. And like I said, these are easy points. Okay, so complex carbohydrates, we've got two types. We've got glycogen and we've got starches. Okay, so glycogen is the storage form of glucose. Okay, important thing to remember when working with any population: what is not used, you don't lose it. Your body stores it. Okay? It's a survival mechanism. It's an evolutionary thing. Okay? But, so if it doesn't use it, it's going to store it. So this is where balancing, and once fat cells are created, they do not get destroyed. Okay? You can shrink them in size, but naturally there is no way to lose them. Okay? If you want them removed, that's a different process, and it can't be done naturally. Okay, so we can shrink adipose cells, but we can't. They're the only cell in the body that isn't actually destroyed. Okay, that's a problem. All right, so glycogen is a storage form of glucose. Okay, limited supply in meat, no supply in plants. Okay, main storage places, primary storage places, liver and muscles. Okay, this is where our body taps for that first burst of energy. Okay, up to about a minute and a half. Okay, highly branched structures means they've got easy access to lots of energy. Now I think we've got a picture coming up where it shows you show you the difference between the starches and glycogen. So you'll see that in a second. If there is excess, it gets converted to fat. Okay, so once that storage within the liver and the muscles is used up and there's no more room, then anything extra goes to fat. Okay, bundle it all together, squish it all together, turn it into fat. She'll be right, mate. Okay, starches. So these can be branched. So in the case of, we've got an example here, amylopectin, or non-branched in the case of amylose. Okay, so remembering our benefits of a branched protein or a branched carbohydrate or a branched anything is that it's got multiple access points. Okay, if it's non-branched, if it's linear, then it's only the ends that can be accessed. Okay, so it's a much slower burn. Okay, storage form for glucose in plants. That's your starches. That's why things like your wheat products and that sort of thing, your vegetables, that's why they're such good, so good when it comes to things like fiber and energy storage. Okay, and it's, as we said, obtained from plant sources like your grains, your rice, tubers, so things like potatoes and things like that. Okay, cool. All right, so intolerances. So we've got fructose intolerance. Okay, so you do get bloating, gas, you get gout, non-alcoholic fatty liver syndrome, or fatty liver disease, sorry, using old terms. Increase in uric acid levels, so burning pee, you get kidney stones. So fructose is absorbed in the small intestine, as we know, metabolized in the liver. Any that isn't metabolized will ferment in the gut, and that's what causes the problem. Okay, so if it isn't absorbed in the small intestine, it goes in the large intestine. As we know, it's not absorbed there. So it just sits there and sort of rots, and that's part of the problem. Okay, lactose intolerance, really, really common thing for a lot of people. Okay, so remember it stems from lactose, or galactose, sorry. It's insufficient breakdown of lactose due to the lack of lactase or the inefficiency of lactase, which is the enzyme, yeah? So excess, again, if it's not absorbed in the small intestine, if there's not enough there to break it down on its pathway through, it's going to sit in the gut, in the large intestine, it's going to ferment and it's going to cause problems. Okay, which is where you get your bloating, your pain and your diarrhea. All makes sense, doesn't it? All right, let's go. So fibers, so we've got 3 types of fiber, technically, okay? Soluble fiber, insoluble fiber, and resistant starches. They're not technically a fiber, but they behave as one, okay? So insoluble fibers and resistant starches contain cellulose, which resists breakdown by water and digestive enzymes. Basically, there's certain things our body just can't process. Okay, soluble fibers dissolve in water, they become a viscous gel, and that's fermented in the colon and then transported out as much as it can be. Okay, so understanding that most fibers are not absorbed. Okay, that's not what they're there for. They're there to provide structure. All right, recommended daily fiber intake. You may or may not need to know this, so make sure you've got a vague idea. 20 grams for a male, 25 for a female. Too much fiber without sufficient fluid can cause you problems, but there is technically no upper limit. Okay, if you have excess fiber and not enough fluid, you get constipation. This can be a bad thing. All right, so you need a good balance. All right, so how does it all work? So you'll find this picture in the text, in Understanding Nutrition. You'll find similar pictures around the place. So you need to know this. Okay, this is important. Guarantee you that there will be questions on this in the exam on how starches work and how fiber works. Guaranteed, set in stone, it'll be in every exam because it's that important. Alright, so what we've covered, so we're calculating acceptable macronutrient distribution range and the energy calculations that flow on from that. Okay, so we looked at carbohydrates, simple versus complex carbs, and we looked at the 2 main intolerances. And then we've also looked at fiber, different types of fiber, and what are the health effects of it. There's a lot in that, but don't stress. You will cover this multiple times in the next in your 13 weeks, yeah? So pop quiz, hot shot, let's go. Okay, so what is maltase made from? Or correction, maltose made from? Okay, so remember, that was the 2 glucose molecules, yeah? Or two glucose gives you a maltase. Maltose, sorry, good God. Too many A's and O's and those and them's. Okay, AMDR, acceptable macronutrient distribution range. Okay, your AMDR for protein, so remembering that was 15 to 25 from memory. Don't quote me on that, but something pretty close to that. Okay, so which fiber can be broken down in the body and where does that happen? Okay, so remember we had soluble fibers which can be broken down. That happens in the large intestine, they ferment in the colon. Okay, understand the process and the flow and where things happen. And what is glycogen? So glycogen, if we remember, is the storage form of glucose. Alright, and that be that. Drinks break. Alright, see you back for the next one. Okie dokie. So, welcome back from your break. Alright, so next one, section 4. So this will be about week 4. So we're talking about carbohydrates. So how does blood homeostasis work? How do we metabolize carbohydrates and what happens when we do? Well, basically what's going on there. What factors affect what they call the glycemic index and what is it? Okay, and what are alternative sweeteners and how do they influence our choices? Or how should they influence our choices? I'll be completely honest, I'm not a huge fan of alternative sweeteners. Use a sweetener, don't use a sweetener, whatever. They bring with some interesting risks, so we'll look into that. Blood homeostasis, so it's regulated by two things, insulin and glucagon. So we've all heard it, well, chances are you've probably heard about insulin, because that's what is involved when we're talking about things like diabetes. A normal pre-meal blood sugar level is around about 4 to 6 millimoles per litre. Okay, so insulin triggers the uptake of glucose into the liver and the muscles when the blood glucose level rises. So blood glucose level goes up, that triggers insulin, or the insulin then triggers the uptake of blood glucose into muscles and liver, and then consequently once those are full, then storage goes to fat, obviously. Glucagon triggers glucose release when additional glucose is needed. So basically this is what says to the body, hey, that stuff that you stored before, look, hey, I need that. Can you please, get some out of the bank because we've got some work to do. Okay, both hormones are released from the pancreas. So the pancreas is basically what's governing what the hell's going on, and that's what we need to know there. This diagram here, okay, you will come across this in the book. There's similar diagrams all throughout the internet, this sort of thing, but you need to understand this pathway and what's going on there. Yeah, so we eat, our blood, the blood glucose begins to rise. High blood glucose stimulates the pancreas to release insulin, which triggers the uptake of glucose into muscles, liver, and then eventually into to be broken down into fat to be stored as glycogen. So insulin stimulates the uptake, that's all happening, that's all good. If the blood sugar drops too low, then glucagon is released, and then that triggers the body to release the stored glucose back into the bloodstream so it can be used. Okay? Gotta understand that, gotta understand what's happening there. And again, all controlled through the pancreas. Gotta know that. Okay? That might be in the exam, as they would say. Yes, it will be, or something similar to it. Okay? So processing of carbohydrates. So food, carbohydrates basically, and the rest of the stuff is eaten. So the carbohydrates is then digested and broken down, as we spoke about before. And what we're looking for is glucose. Okay? Glucose peak triggers the insulin release, which then triggers the uptake of glucose into liver, muscles, and then into fat. Okay, excess glucose obviously is stored as glycogen in fat. Got to remember that. Okay, blood glucose levels decline as we are post food intake, and as they decline, the body looks to maintain that level of blood glucose, so it triggers the release of glucose from liver, muscle cells, and then eventually mobilization of glycogen to create further glucose if needed. Okay, so that's what we need to remember there. Yeah, around and around and around it goes. Once the stores in the liver and the muscles run out, then we'll start to mobilize stuff from fat cells. Well, break down triglycerides, glycogen, etc. Get into that later on. Hypoglycemia, so low blood sugar level. Okay, hypo, low, hyper, high. Important to understand the difference. So we've got type 1 and type 2. Okay, so type 1, in the case of type 1, the body, that's a genetic thing, body doesn't produce insulin. Important to know. Okay, in type 2, the body doesn't respond to insulin. That is a developed condition. So type 1 is genetic, there's nothing they can do about it. They were born that way. Okay, type 2 is developed over time. Okay, so that's what we talk about type 1, type 2 diabetes, that's what we're talking about. Okay, so type 1, like we said, hereditary condition. Signs and symptoms: thirst, frequent urination, fatigue, and weight loss. Okay, potentially they can go into a diabetic coma. Okay, it's scary as hell when it happens, particularly if you don't know that person's condition. You're like, what the? They just get really, really, really lethargic and then poof. Most people are on top of this, okay? But be aware, if you do have friends or family members, well, if you've got family members, you know about this already. If you get friends and colleagues and that who are type 1s, they need to maintain their blood sugar levels, okay? Otherwise, it can have real problems for them. Okay, type 2, so the body doesn't respond to insulin in the same way. So it's usually preceded by insulin resistance, and it's a developed condition. Okay, so signs and symptoms: excessive hunger, weight gain, that sort of thing. Okay, and consequently with that, a lot of the time cardiovascular issues happen as well. All right, so just be aware of that there's the two things. And one is characterized by weight loss, the other one's characterized by weight gain. Okay, both are potentially problematic. The treatment for the first aid treatment for both is the same. Okay, if they crash, then sugar. Okay, slowly. If they're unconscious, obviously don't give them anything to eat or drink. Okay, DRABC, urgent medical aid, etc. Okay. And remember, you can't give a person insulin injection, they have to give it themselves. Alright, so glycemic index. Okay, so this is the thing you see, like high GI and low GI food, and you know, blah blah blah. And everyone sits there like 90% of people wouldn't be able to tell you what the hell that actually means. So the glycemic index, that number that's in the GI, okay, that is the area under the 2-hour response curve for 50, usually for 50 grams of carbohydrate. Okay, so it's a graph as to how fast or how slow any given food is effectively burned as a carbohydrate, as a source of energy. Okay, the higher the GI, the faster it burns. Okay. The lower the GI, the longer the time period it's stretched over, okay? So it's a more sustained burn as opposed to a quick boof, a quick short flash, okay? So that's what we're looking at, okay? So it's the area under the 2-hour response curve. So where we see the graph showing how fast it burns and drops off, okay, we're looking for a nice, slow, steady burn over a prolonged period of time. We want sustained energy from our food. We don't just want to get that quick sugar hit within our 2-hour response curve. We feel great, then we crash like nothing. Okay? So, low GI foods are your grains, your whole foods, that sort of thing. Your high GI foods are usually your highly processed foods. Okay? Lots and lots of simple carbohydrates. Classic example, white bread. Okay? So low GI, we're talking about low GI, we're talking under 55. Okay, high GI, we're talking over 70. And obviously, medium, middle of the road, 55 to 70. Okay, so the numbers to remember, 55 and 70. 55 and below, low GI. 70 and above, high GI. Okay, might want to remember that. Okay, so that's the, you'll see this diagram in your book. and you'll see it around, etc. So at one end of the spectrum, you've got white bread. Right at the other end of the spectrum, we've got things like peanuts and soybeans and that sort of thing. Okay, so again, it's the area under the 2-hour response curve. Okay. Okay. So then we talk about something called. They'll talk about something called glycemic load. Okay. So this is a percentage. Okay, a percentage of your load that comes from a particular GI food. Okay, so you can have a high GI food that's only accounting for a low percentage of your daily energy intake, which is not necessarily a bad thing. Okay, so it's used to determine how much of your glucose load comes from a particular source. It's a percentage value. Okay, so the formula is there. Okay, so they will provide this for you if you need it. All right, so glycemic load basically is the carbohydrates in grams multiplied by the glycemic index for that carbohydrate divided by 100. Okay, so watermelon, for example, is a GI of 72. So it's a high GI food, but it's got very low weight. Okay, so low mass, high GI, smash the two together, we get 360 divided by 100. It's only 3.6% of that person's daily glycemic or GI load. Okay, glycemic load. Okay, probably not going to come up in an exam, but worth being aware of, because if you ever get asked about it as a professional, it's good to understand and to know, so that you're going, yeah, but yes, the GI in that food is high, but it's not necessarily unhealthy. Okay, watermelon is fantastic, it's awesome. It's a high GI food. Oh my God, it's a high GI food, it's bad. Not necessarily, no. Well, you know, it's at the upper end of the mid part, you know. It's got a high GI, I should be eating something like... don't stress, man. It's not... Okay. View it all through the lens of knowledge. Understand what it means. Okay, so sugars and sweeteners. Right, so you'll see sugars, and some sugars will be described as natural. Yeah, that's... honey's natural, kind of, but it's still a sugar. Okay. So your best sources of natural sugars are from fruit, veg, honey, etc. Okay. It's easy to overconsume when you talk about refined sugars. So things like your soft drinks, like your energy drinks, like chocolates and candy bars and that sort of thing. The links to obesity, behavioural issues that you can have with sugars. Some of the behavioural stuff's still a bit meh, all over the place. It's difficult to do really good research in that sense. Energy without nutrition is what we're talking about when we're talking about empty calories. Okay, so I can have a chocolate bar. It's got plenty of energy, but it's got virtually no nutritional value to me in terms of other benefits. So vitamins, minerals, etc. Protein, well, not protein, sorry, but fiber, etc. So they are basically empty calories. Good for that short, sharp burst of energy. Not much good for anything else. Okay. Sweeteners, they can be natural or they can be artificial. They have little to no calories. Stevia is a common natural sweetener. Some people think it's awesome. It's about 10 times sweeter than sugar, so you really don't need very much. You get things called saccharin and aspartame. They are artificial sweeteners. What do they call it? Sugarine, this sort of thing. So yeah, they've got their benefit is they've got no calories, so they've got no energy value. They just provide the sweet stimulus, which may or may not be a good thing. Okay, sugar alcohols, so they're technically not a sugar, but it behaves as a sugar, and it contains more calories than sugar, or more kilojoules per gram than sugar. Because remember, cast your mind back to those numbers, 17, 17, 37, 29. Alcohols 29 kilojoules per gram. So your sugar alcohol, while not a sugar, still contains kilojoules. Okay, so when they say it's natural, well, it is, and it's sort of not. And when they say it's not sugar, well, they're kind of telling the truth, and they're kind of not. So just be aware of that. Examples are things like sorbitol, mannitol, the one you'll find quite often, xylitol. That's a popular one in a lot of the sports drinks. Okay, so it's not technically a sugar, but it behaves as a sugar, and it carries the kilojoule load of an alcohol, so 29 kilojoules per gram, as opposed to your normal your simple carbohydrate, your sugar, which is only 17 kilojoules per gram. So always be aware of what it is. If they're saying something's, if they're saying it's some sort of miracle cure, start asking questions, okay, and looking at why, exactly how this is happening. So issues with sugar and sweeteners and all these things, dental caries, so don't know why they call that, cavities, gum disease, those sorts of things. Insulin resistance and insulin desensitization, that's one of the big problems with your artificials. Okay, the sweetness can trigger a response which is over the top because there's not actually the glucose there for the insulin to transport. So it's kind of like the boy who cried wolf. Okay, you keep hitting the alarm button saying, hey, there's all this glucose here we've got to get rid of. Problem is, well, there's not actually all that glucose there that we need to get rid of, so the insulin response starts to decrease. Okay, the other problem you can have is addiction, okay, and desensitization to sugar and sweetness and that sort of thing, and which means you need more and more over time. And changes to your gut microbiome, okay, what we eat affects how the internal mechanism functions. There's a lot of research going into this. If you're lucky enough to get Klaus at your as one of your lecturers for this unit, he will go into this in depth. He's a huge, this is his thing, this gut microbiome. There's him and a few others around who are doing a lot of really, really cool work in it. So definitely ask questions about it. They're really great. Great sources of information for this. Okay, so what do we cover? So we just looked at how blood homeostasis works. We looked at how we metabolize carbohydrates and what happens when we do. So we talked about the peaks in glucose levels and then what happens if we don't have enough. So we looked at glycemic index and also what it is, and also glycemic load, hand in hand with that. And then finally we looked at the alternative sweeteners and how sugars and sweeteners, how that can influence our food choices, yeah? And some of the problems that can be associated with it. All right, so questions. So maltase is used to break down which type of disaccharide. So this is going back to the previous lecture. And you will find that occasionally they'll jump backwards and forwards in things. So it's used to break down maltose, okay? So what's the role of dietary fiber? Okay, fair enough. So that's in regulating your bowel movements and that sort of thing, and controlling the pace of absorption. Hydrolysis, how does that affect digestion or carbohydrate digestion? So that's used for the breaking of bonds, so that proteins can be broken down, proteins and disaccharides and complex carbs can be broken down to form monosaccharides, which can then be transported and used. Which is better in terms of sustained energy when we're talking about a high GI or a low GI food. So remembering the glycemic index, the GI, is the area under the 2-hour response curve. So a low GI food has a less area in that 2-hour window. So that's going to give us a more sustained burn of energy. So it's a lot better bang for buck. All right, cool. All right, have an uplifting break. So you should always start a day with a lift, and you should always lift heavy. And the best way to start a lift is to lift a crane with a crane. So yeah, there you go. Alrighty, so we're into section 5 or week 5. So looking at lipids, look at fats. So we're going to look at what is a fatty acid, where and how do we get fatty acids, why do we need them? Because this is something everybody harps on about. Oh, no fat, fat's bad. You need a certain amount of fat. That's part of life. Okay, understanding what amounts you need and how far you can push the envelope, that's important for us as coaches. Okay, what happens when we have too little or too much fatty acid, and away we go from there. Okay, so what's a lipid? Basically, a lipid covers fats of all types. Okay, so broadly there are three main types of fats or lipids that we're talking about. We're talking about triglycerides, phospholipids, and sterols. Okay, and we'll go through each of them in a bit. Okay, so basically, triglycerides. This is what we think of when we say fats or oils. Okay, you've got saturated, unsaturated, polyunsaturated, trans fats. You've heard these terms before, yeah? That they're generally what we're talking about when we're talking about fats and what everyone thinks of. They're talking about triglycerides. Okay, there are essential and there are non-essential fats. Okay, some of them you need, some of them you don't. Okay, wide range of uses throughout the body. Okay, and we'll go through those in a little bit. So phospholipids. Okay, so these are a specific type of fat that's used to transport lipids across the cell membrane. Okay, they're basically a transport thing. That's the way they work. Okay, so they've got a hydrophobic tail and a hydrophilic head. Okay, it's water, hydrophobic, water scared of or averse. Hydrophilic means they like water, so water liking, water appreciating, water attracted to. Okay, so the way they work is that the tails facing together and their heads are on either side. Okay, that's basically how it works. All right, so that's how they form a barrier around certain things, which we'll go into. Okay, so found in eggs, liver, and soy. Okay, so there are positives to these things. Okay, and then you have sterols. So sterols typified by their ring-like structure. Okay, anything ending with a suffix erol, erol, is a sterol of some form. The most common one we hear about all the time, cholesterol. Okay, that's a type of sterol. It's a type of fat, as you've probably heard in the media multiple times. Okay, you need an amount of it. It can be used for lots of cool stuff, but problem is if we get too much, then we're going to have some problems that come with that. All right. So triglycerides in detail. So these are basically derived from a 3-carbon glyceride that hangs. From each of that hangs a fatty acid chain. Okay, so the length of the fatty acid chain determines whether it's short, medium, long, short chain fatty acid, long chain fatty acid, etc. Okay, so when we're talking about short, we're talking 1 to 5 carbons. Okay, so all of this is referenced back to your carbons, yeah? Medium, 6 to 12 carbons long, and a long chain fatty acid, 12 plus, all the way up to 21 carbons. But all stemming from the 3-carbon triglyceride. Okay? That's important to remember. Okay? The 3-carbon glyceride is what makes it a triglyceride in the first place. Okay? So the double bonds determine whether something is saturated or not. Okay? If it's saturated, then there is no double bond. It's all single bonds. That means every available hydrogen that can be on it is. Okay? It's got its full hydrogen complement. Okay, a mono unsaturated. Mono meaning 1. Unsaturated meaning it's got a hydrogen free. Okay? Potentially. Okay? But it has 1 double bond. If there's not a hydrogen, then there must be a double bond somewhere. If it's missing more than 1, if it's missing 2, then we have we could theoretically have you might say a diunsaturated, but we don't. We say a polyunsaturated. So more than 1 becomes a poly. So 1 or more double bonds, more than 1 double bond if it's poly, then there has to be a shortage of hydrogens. Yeah. The first double bond is the point of unsaturation, and it's counted from the methyl end. We'll see that in a minute. There we go. Beautiful. So when we talk about the methyl end, we're talking the end with the carbon and the 3 hydrogens. Okay. The other end will have the acid. Remember, it's a fatty acid. Yeah. So at the other end, we're going to have a carbon with an oxygen, with a double bond, and oxygen and a hydroxide, single bond. Yeah. So in the middle, we could have anything up to, like we were saying before, 21 carbon atoms. So we could have a further 19 carbons stuck in between these two ends. We always count the double bond from the methyl end. So start from your CH3 end and count your way in till you get to the double bond. How many carbons that is, that's it. Okay? Right, so that's blah, blah, blah. Right, examples. Boof. There you go. So here on the top, we've got a saturated fatty acid. So there is no double bonds in the carbon chain, and all available points are taken up by hydrogens. Okay? Unsaturated fatty acid, we've got a double bond in there. Okay? We can see that double bond smack dab in the middle, and they've got a sort of kinked formation to them. Okay? And we're counting from the methyl end, which is, well, as I'm looking at it, it's going to be the right-hand side. As you're looking at it, it's probably going to be the same again, right-hand side. So we go 1, 2, 3, 4, 5, 6, 7, 8. And so that bond is on the 8th carbon. Okay? Don't stress too much about it. You'll get to know all this stuff as you go through. But they're not going to ask you about that. It's more important that you understand what the triglyceride is, how it works. Okay, which is what we're getting into now. So what's that got to do with triglycerides? Basically, so a fatty acid is combined with a glycerol to form, that should say form, a triglyceride via condensation. Okay? So basically, the glyceride, the glycerol molecule combines with the fatty acids, releases water, and you end up with a triglyceride as we see there. Okay, that can then be broken down by the addition of water. So we add water to it, and this can help break it down, given that we've got the right kind of enzymes and stuff to drive that reaction. All right. So stearic acid is saturated fatty acid. That's the version of it there. Then we get something that's an essential fatty acid called linoleic acid. It's a polyunsaturated fatty acid, meaning it has more than one carbon double bond. Okay, so you see them there on the bottom. We've got our linoleic acid with 2 carbon double bonds. Okay, and if we count from the methyl end, we've got 1, 2, 3, 4, 5, 6 carbons in from the methyl end. So this is an omega-6 fatty acid because the double one is on the 6th carbon. All right, important to understand. That's the biochemical abbreviations down the bottom. So you've got C18, which is stearic acid. Then you've got C18, 2 double bonds, N6, 6th carbon in, or an omega-6 fatty acid, as it's more commonly called. Right, cool. Eicosanoids. Okay, they behave like in hormone-like ways. They require adequate long-chain fatty acids for synthesis. So the body makes these. These are essential fatty acids. Okay, but if there's not enough fatty acids, then it can't make them. Okay, their deficiencies are rare, but they can happen in children when you get parents and others sticking kids on low or no-fat diets. Okay, that's potentially not healthy. Okay, kids grow and change and need bucket loads of energy. Okay, chopping out the emergency energy reserves is not the best idea you're ever going to have in your life. Okay, examples, so prostaglandins, so they're for inflammation and contraction of muscles. Thromboxanes, they help with blood clotting and blood pressure regulation. My English is terrible today. Threins, sorry. They're inflammatory mediators, so they stop you from swelling too much or too little. Okay. Properties of fat, so like we were saying before, saturated fats and unsaturated fats. So generally speaking, saturated fats, they are the ones that are solid at room temperature. They have the maximum number of hydrogen atoms that they can, and they tend to resist oxidization because they're quite happy as they are, thank you very much. There's no double bonds, there's no weaknesses to exploit. Okay, there's nothing that's really going to lend itself to a reaction. Okay, so unsaturated fatty acids, or unsaturated fats, they're normally liquids at room temperature. Okay, they help reduce spoilage, which is why they're quite often used in like manufacturing food products. These can often be used to form fatty acids or trans fats. Trans fats will go on to, I think in the next slide, if I'm not mistaken. No, okay, right. Well, we will go on to trans fats, but don't stress about that. So essential fatty acids, right. So they cannot be made by the body. They must come from your diet. Once we've got them in, then the body can synthesize and work with it. Example, linoleic acid and alpha-linoleic acid. They are the two big ones, omega-6 and omega-3. You need enough of these, and unfortunately can't actually make them, need to get them from our diet. If there's insufficient presence of these in our diet, then we can have growth and developmental issues, which is not cool. Okay, non-essential fatty acids. So you need to know linoleic acid and alpha-linoleic acid, yeah? Got to remember that. Non-essentials, okay, mostly to do with energy storage. They can be used for structural and repair work where needed, but their main thing is storing energy. That's what fats are for, predominantly. Okay, specific note on trans fats. So this is what I was getting at before. So on the left, you've got your ordinary fatty acid, okay, with its double bond, and it's got that interesting sort of V-shaped type structure. Then on the right, you've got a trans fat. Now it's still got a double bond, but the hydrogens are opposed, and it's all one nice straight line. That's not a good thing. Okay, so it's similar to an unsaturated fatty acid, but it behaves as a saturated fat in the body. So it doesn't have the positive benefits, it basically just takes up space. Okay, phospholipids. So the main role is in transport of lipids across the cell membrane. This is what we were talking about before. So we've got the hydrophobic heads and hydrophilic heads, hydrophobic tails. And they're involved in forming that barrier. Okay, the best known of them is lectin. Okay, the hydrophobic and hydrophilic ends make them ideal as emulsifiers for fat transport. Okay, so they can basically surround fat molecules and help transport them through the cell membrane. Liver synthesis. The liver synthesizes all the lectin a person needs. So we don't have to get this from our diet. There's no benefit to this in finding lectin supplements for some reason. That's not going to improve your situation. This all comes from your diet. Okay, your body can make this naturally. You don't need to add to it. Okay, under normal conditions. Okay, sterols, structural component of cell membranes. Pretty much, this is it's building block stuff. Okay, starting material for bile, vitamin D, adrenal and sex hormones. Okay, the best known of them is cholesterol. Okay, liver produces around about 800 to 1500 milligrams of cholesterol per day. Again, don't really need to get it from your diet, but we can. And unfortunately, we get far too much of it most of the time. Additional dietary cholesterol can cause arteriosclerosis. That is hardening of the arteries. That's bad. Okay? Boom. So, sterols in the body. You will find this picture or something similar to it showing you where different sterols are used throughout the body. And it didn't come up in my exam, but it's probably a good source for an exam question. Okay, so how does it all work? So basically fat is broken down by bile combining with its monoglycerides in the small intestine. Okay, so bile was released from a gallbladder, remember? And this forms micelles, okay, which are absorbed across the barrier and they go to form a chylomicron. okay, which is the largest form of fat transport, fat transport vessel that goes into the lymphatic system, and away it goes from there. So we start as a chylomicron. As we're going around, the body breaks off cells or fat to serve as to facilitate the energy needs or whatever else it happens to be using the fat for, and then as it passes through the liver each time, it is broken down even further. So we get down to a very low density lipoprotein, then a low density lipoprotein, and then finally down to a high density lipoprotein. So this is 50% protein, and this is what they consider to be, this is what you're talking about when you're talking about good cholesterol. You'll hear that term in popular culture these days. Okay, so but that's what they're talking about, high density lipoproteins. Okay, they're the good ones. Low density lipoproteins, very low density lipoproteins, and chylomicrons, they're not so good. Okay, cool. All right, so issues with fat. So if we have too much fat, we get problems with obesity. We get arterial hardening. Remember, that's arteriosclerosis. We get increased blood pressure, fatigue, general health decline. We get mental health concerns. There's been links to cancer. And the list just keeps going. Okay, it's not a great game. Okay, too little fat. This can be just as problematic. Okay, so in children we can get growth and development issues. With athletes we get prolonged recovery times. We start to see immune issues, cartilage, ligament, and tendon issues. Okay, muscle pains, growing pains, all sorts of horribles. You know, the slow recovery rates, fatigue, because fat supplies 60% of our body energy. If we don't have enough fat, well, we don't have enough energy stores to keep everything running. Okay, and we get hormone, behavioral issues, mental health issues. Yeah, so be aware that too little fat is a problem. Too much fat is a problem. We got to have a nice even balance, yeah? Acceptable levels, so total cholesterol less than 4 millimoles per litre. Low density lipoproteins less than or equal to 2.5 millimoles per litre. Triglycerides less than 2 millimoles per litre. High density lipoproteins anything over 1 millimole per litre. So if you haven't figured it out already, you add those together, you end up with way more than the total cholesterol of 4 millimoles per litre. Okay, so figure that one out yourself. So this just explains how chylomicrons work, okay, and basically the structure and how, as it flows through, we go from our chylomicron, which has got a lot of triglyceride in it. By the time we get down to a high density lipoprotein, we're mostly protein, some cholesterol, but minimal triglycerides. Okay, so it's got capacity there to actually absorb and move other triglycerides, which is useful. Okay, chylomicrons is formed in the small intestine. They provide transport for digested lipids around the body. Each circuit increases the density of protein and improves its efficiency. Okay, so we get better and better each time. Okay, so that's the pathway for it. That's how it works. Okay, nothing on this was in my exam, but don't take my word on it. This is an area that's really, really good for questions. Okay, so question time. Basically, what's a trans fat? So a trans fat is an artificial fat. It has a similar appearance to an unsaturated fat, but it behaves as a saturated fat. So it's not actually giving us any of the benefits. Okay, so which of these is considered a healthy lipoprotein? This one was in the exam. Okay, so it's a high density lipoprotein, HDL. Okay, lipoproteins do what? Predominantly they're involved in the transport of fats around the body. Okay, two types of essential fatty acids, remember, linoleic acid, alpha linoleic acid. Okay, gotta know them. Okay, and how is a triglyceride formed? So it's chains of fatty acids attached to a 3-carbon glyceride. Okay, gotta know that, gotta understand that. All right, cool. All right, take a break and we'll hit it up afterwards. Okay guys, hope you had a good break. Righto, so where we're at the moment is we're moving on to section 6. So this is week 6 of your semester, yeah? Alright, so proteins and amino acids. basically what we're looking at is how proteins are formed. And what's important here is we're not just talking about like proteins like as in your protein shake. Okay, proteins, there's a lot of different functions in the human body. Okay, so how are they formed? How are proteins and amino acids digested, absorbed, and metabolized? Okay, that's important. If you can understand how this works, then the whole protein thing starts to make a lot more sense. What are food sources of protein? And what are positive and negative effects of protein? Because like everything, if there's too much of one thing, we're going to have a problem. Okay. All right, moving on. Right, so how are proteins made? So proteins are made up from amino acids. Okay. And what's important here is that they're made in the body. Okay, so your protein shake isn't actually doing what you think it's doing. Okay, it's simply providing material for the body then break down to build what it needs. Okay, there are 20 amino acids used. Okay, and 9 of them are essential amino acids. Okay, so by essential means they can't be made or synthesized in the body in sufficient quantities. Okay, so the process, how this whole thing works. We consume protein, okay? So that might be meat, eggs, fish, whatever, or your protein shake, okay? With all its touted benefits. So the body then breaks down the protein into amino acids, okay? It then takes those amino acids and builds them back into the protein that it needs. Okay, so even if you were to take exactly the right protein that your body needs, your body would still break that down into its component amino acids and then put it back together the way it needs it. Okay, that's how it works. Okay, different proteins have different levels of absorption. So your animal proteins, we absorb 90 to 99% of those. Okay, we can break almost all of it down and it becomes useful to us. Soy and legume proteins around about 90%. Vegetable proteins 70 to 90, depends on the vegetable. Okay, so not critical to know those numbers, but good to know. The most usable for us as humans is animal proteins. But yeah, realistically, the others aren't that far off the pace. We just need to balance it, that's all. High quality versus low quality proteins. Okay, so when we're talking about high quality protein, the high quality protein builds or provides enough of all the amino acids needed to support the body's work. Okay, a low quality protein has the insufficient types or insufficient quantities to support all of the functions. Okay, that's important to remember. That'll be in there, okay? Something like that. If it's not in your exam, it'll definitely be in your quizzes, guaranteed. Okay, so essential amino acids, don't worry, you're not expected to remember these. And if I learn to spell essential-ish amino acids, okay, so we're essential and we've got also some that are conditionally essential. So our essential ones, our 9 essentials: histidine, isoleucine, lysine, methionine, phenylalanine, good grief, learn to speak, threonine, tryptophan, valine. You won't be expected to remember all of them yet. I wouldn't be at all surprised if you expected to remember them later on, but in semester 1, no. Conditionally essential: arginine, cysteine, glutenine, glycine, proline, and tyrosine. About the only thing you do need to remember is that there are 9 essential amino acids. Okay, but otherwise don't stress too much about it. Okay, so proteins, how are proteins formed? So proteins are formed using peptide bonds. Okay, amino acids bonded together to create proteins. Okay, and they layer over at different points. So we've got 2 amino acids with bonded together. We've got a dipeptide, 3 tripeptide, anything 4 or more, we got polypeptide. Okay, don't stress too much about it, just need to understand what it is. This is the important bit though. Okay, so we'll take an example of insulin. It is a protein, okay? Haha, know that. So it's also a hormone. So the hormones are also proteins as well. So everything we use pretty much that makes everything go is an amino acid base. Okay, so they're made up of amino acids to form proteins, and away we go from there. So each of those little circles there, so in the case of insulin, there are 51 amino acids and they're in 2 polypeptide chains. Okay, these chains are linked by 3 disulfide bridges between the cysteine amino acids. Okay, so that's the S and S that you can see bridging across between the little circles which are marked CYS. So each of those little circles represents an amino acid. Okay, the order in which those amino acids are put together is critical. If that is wrong, then this protein will not do what it's supposed to do. Alright, so bearing in mind this is an incredibly simplified way of looking at this, but it's a really good way to visualize what's actually going on. Okay, so all these different amino acids, it's basically just it's a cooking recipe on steroids. Okay, so every single amino acid fits together with every other amino acid, which is then bonded across together to form this structure that tells the body what to do and how to do it. Okay, so in very, very, very simple terms. Okay, so there is another way we can do this. Okay, so if the body can't get exactly what it needs, it's got a plan B. There's always redundancy. Okay, so the plan B pathway is called transamination. So this is where your body can take a ketoic acid, shift the functional group, which is the side group, and then form and put on another amino to change its function, basically. So excess amino acids can be removed via the liver and kidneys. Ketoic acids can be used to shift functional groups around and to change the structure and function of an amino acid. Okay, so very rarely does it get stuck into a position where it can't find a way around a missing or incorrect amino acid. You know, if it doesn't have enough of something, it's usually got a way to make what it needs. It just may not be as efficient as we would like. Okay, so the waste products from this process, you're talking about water, carbon dioxide, and urine, basically. Okay, so as we can see, basically what happened, that's the diagram on the right hand side there. You've got your side group, you've got your ammonium, and basically it takes the ammonia off, changes it to a ketoic acid, then it can change its structure and add the ammonia back on to turn it back into an amino acid. Okay, so the pathway of digestion. So in the mouth we go through gross breakdown of material. So this is our mastification that we talked about before. In the stomach, pepsin and hydrochloric acid denature the protein, basically breaking it into polypeptides. Okay, that's phase 1 of the breakdown. In the small intestine, the polypeptides are broken down further into specific amino acids by different proteins or by protein specific enzymes, proteases. Okay, so remembering each thing is only broken down by the specific enzyme that targets it. Otherwise, it just sits there and does its thing. If there's insufficient enzymes to work with a certain amino acid, then you're going to have problems and you're going to have a shortage there. Okay, so this diagram on the right, you're going to see this in the book. You need to know it. You need to have your head around this and how it works. Okay, what's happening when? Okay, so the pepsin and the hydrochloric acid denature proteins into polypeptides in the stomach. In the small intestine, the polypeptides are broken down into amino acids by protein-specific enzymes. Okay, got to have your head around that. That's important. Metabolism of proteins. Okay, so amino acids enter the body via absorption in the small intestine, like virtually everything does. Okay, once in the body, cells reconfigure the amino acids into the types of protein they need. Now that information comes from the DNA that's contained in each cell. Okay, so you'll get into this in Anat and Phys, but that's the important part to understand. The DNA holds the instructions of what this has got to look like. All right. A single flaw in the sequence can have crippling effects for a person. Okay, and we'll look at an example of that very shortly. Okay, right now so hemoglobin is a protein. Okay, so hemoglobin, if you're not familiar with it, they're your red blood cells. Okay, so sickle cell anemia is the result of a single incorrect amino acid placement in the chain, in the protein chain that makes up hemoglobin. That's all it is. It's one change. And if you look down, we've got normal hemoglobin there, so we've got VAL, HAS, LEU, THR, PRO, GLU, and a GLU. In a sickle cell anemia hemoglobin, everything's the same except for the second last amino acid, where it's a VAL instead of a GLU. That one thing in the wrong spot is enough to cause a condition which will affect that person for the rest of their life. It affects their cell's ability to carry oxygen, and for that person, it changes the shape of it, changes its behavior, and now that person is going to struggle. Okay? That's how critical this is. And that information is contained in the DNA. Okay? So it's basically like having a bad recipe. If you've got a bad recipe and you put the wrong ingredients in, guess what? And you put them in the wrong order, it ain't going to taste right. Okay? So positives and negatives. So too much protein. Okay, so anything that is not required, surprise, surprise, is turned into fat. Remember, 17 kilojoules per gram. Okay? Can place additional strain on liver and kidneys. Okay? Every system in our body has a certain threshold. There's only so much you can load into the system before it becomes overloaded. You can get problems with osteoporosis. You can get problems with cancer. You can also get liver disease and or kidney disease, and all sorts of other problems. Okay, so remember, too much of anything's not a good idea. Okay, this is where your calculations and your diet is critical. Okay, diet first, then if we can't get the quantities and types that we need in our diet, then as a last resort, then we look at supplementation, not a moment before. Okay, too little protein. Okay, you get hormone production issues, you get structural problems with bones and muscles, you get cognitive function issues, you get light sensitivity, or can get light sensitivity, slower healing and recovery rates, that's the big one that a lot of people notice, and also something called protein energy malnutrition. Okay? You don't need to know all of that, but you need to know some of it. Okay? Okay, protein energy malnutrition. Sorry, protein energy? Yes, protein energy malnutrition. Okay, two types. Very, very rarely seen in Western cultures, but you need to know what both of them are. Okay, marasmus, okay, that is prolonged deprivation. Okay, prolonged food deprivation. Okay, literally means dying away, if we go for a direct translation. Okay, the other one is kwashiorkor. Good grief. Sorry, I don't speak that language, so don't take it personally. If I've got that wrong, please forgive me. Okay, that's an acute deprivation, a short-term deprivation. Okay, usually common in older infants and children. Okay, so if we're looking at marasmus, remember, that's a prolonged deprivation over a sustained period of time. Usually common in young children and infants. Severe weight loss, muscle atrophy, balding, wrinkled skin. Their weight's usually less than 60% of their of the age for the average, and they kind of look like a walking skeleton. Okay, so remember that. Okay, so marasmus, prolonged deprivation, they look like a walking skeleton, and obviously they've got all the relevant symptoms that you would expect to see in that sort of person. Okay, where they've got muscle atrophy, they've got really wrinkled, baggy skin, they're underweight for their age, they've got severe weight loss. Okay, that's marasmus. Kwashiorkor, acute deprivation. Okay, short term. Okay, but really severe. Okay, they will get some weight and muscle loss, often skin lesions, edema, and or enlarged liver. But the big giveaway with them is they're skinny with a fat belly. Okay? They're the two big ones. Okay? Marasmus, they just look like a walking skeleton. Okay? The Quashcore, they're skinny, but they've got this fat belly. Okay? So they're the two big giveaways for it. Okay? That's how you're going to remember them. That's the easiest way of doing it. Okay? Good possibility you might need to know that for at least some of the quizzes, if not the exam. Okay, so protein recommended daily intake, 15 to 25% of your total daily energy intake. As a general rule, 0.84 grams per kilogram for males, 0.74 grams per kilogram for females. Athletes, they're saying 1.4 to 1.7 grams per kilogram. Above all, do the maths. Okay, as a coach, you have to know how to balance protein, how to balance carbohydrate intake, how to balance fat intake for the particular times of training or types of training you're doing, and the time of your periodization cycle where you sit or where your athlete sits, and what they need to be doing at that point. Okay, if you're trying to build mass, you need to load differently than what you do if you're just trying to maintain readiness. Okay, so hey bro, we're gonna get a protein shake around here, dude. There's no way in hell. Yeah, okay. Anyway, funny, not really, but yeah, got to find something to put in there. Okay, protein for energy. Okay, so our body has multiple redundant systems most of the time. Okay, so when it's generating protein or energy from protein, the process is known as glyconeogenesis. Okay, glyco, sugar effectively, energy, neo, beginning, making new energy. Okay, or making new sugar, depending on which way you want to look at it. Okay, happens when glucose and fatty acids are limited. Okay, so we've run out of glucose, we've run the fatty acids down as far as we're going to go. Now we've got to start getting energy from somewhere, and the only reasonable source left is our protein. Okay, when you'll see this happen, we used to call it muscle meltdown. Okay, so if you don't have sufficient fat reserves, you've been going way too hard with not enough food, then the body's exhausted all the easy glucose, like the glucose stores, the glycogen stores are gone. It doesn't have sufficient time to be scavenging from fat, and so it goes into this, okay, and it'll start tearing energy from anywhere it can get it. Okay, and what happens basically is that they just collapse. The key to it, when we're doing preparation for selection courses and that sort of thing, is making sure you've got sufficient fat reserves that your body's able to access that. It's not going to completely stop it, but it'll help provide a bit of a buffer. Okay, so the NH2 group is removed and excreted through urine, so that's your urea. Then the carbon backbone can then be used in the TCA cycle, which you'll learn about in this and also in Anat and Phys. You'll go a lot into this. Okay, so the TCA cycle or the Krebs cycle is just the way our body generates energy. Okay, so basically it'll strip the amino or the protein down, and then it'll start using the carbon chain as it would any other carbon chain, so like glucose, fatty acids, whatever. Okay, so questions. Dietary protein is automatically used by the body, true or false? So no, that's false. Okay, doesn't matter what protein you put in, it can be letter perfect for exactly what your body needs. Your body will still break it down. If you ingest it, then your body will break it down and use it. Okay, injections are different. Okay, how many essential amino acids are there? So remember, there was the 9 essential amino acids. Okay, what's a high quality protein? So a high quality protein is a protein that provides all the amino acids that are required in sufficient quantities. Okay, and what determines the function of an amino acid and the subsequent protein? So that is the order in which the amino acids are assembled. Okay, if they're incorrectly assembled, then they're not going to do what they're supposed to do. All right, like we saw with the sickle cell anemia example. All right, cool. That's the end of part 1. So then we move on to part 2, which is the second lot of lectures. So this is basically from now you would hit your mid-semester break. You've got assignments, you'll have mid-semester exams. Don't stress too much about them. What we've just covered is everything that's in them. Okay, that's everything you're going to do, excepting for the food work stuff. All right, so the next bit we're going to cover the second half of the semester, and then pretty much your end of semester exam covers everything from the very start to the very end. Okay, so you need to be across the entire lot. All right, take a break and we'll get on to section 2 very shortly.